I'm going to begin by reading the first page of this handout, and then you will be able to do the clicker quiz. Okay, so this is just another review here of work and power. So the quantity of work has to do with the force causing a displacement. Work has nothing to do with the amount of work that this force acts to cause the displacement. Sometimes the work is done very quickly, and other times the work is done rather slowly. For example, a rock climber takes an abnormally long time to elevate her body up a few meters along the side of a cliff. On the other hand, a trail hiker who selects the easier path up the mountain might elevate her body a few meters in a short amount of time. The two people might do the same amount of work, yet the hiker does the work in considerably less time than the rock climber. The quantity which has to do with the rate at which a certain amount of work is done is known as power. The hiker has a greater power rating than the rock climber. Power is the rate at which work is done. It is the work-to-time ratio. Mathematically, it's computed using the following equation, which we've seen already. Power equals work over time. The standard metric unit of power is the watt. As is implied by the equation for power, a unit of power is equivalent to a unit of work divided by a unit of time. Thus, a watt is equivalent to a joule per second. For historical reasons, the horsepower is occasionally used to describe the power delivered by a machine. 1 horsepower is equivalent to approximately 750 watts. Anybody actually look up the conversion? I think it's 747. For some reason that's 746. Okay. Most machines are designed and built to do work on objects. All machines are typically described by a power rating. This power rating indicates the rate at which the machine can do work upon other objects. Thus, the power machine is the work-to-time ratio for that particular machine. A car engine is an example of a machine which is given a power rating. A power rating relates to how rapidly the car can accelerate. Suppose that a 40 horsepower engine could accelerate the car from 0 to 60 in 16 seconds. If this were the case, then a car with 4 times the horsepower could do the same amount of work in a fourth the time. That is, a 160 horsepower engine could accelerate the same car from 0 to 60 in 4 seconds. The point is that for the same amount of work, power and time are inversely proportional. Equations can be guides to thinking about the relationship between quantities. The power equation suggests that a more powerful engine can do the same amount of work in less time. So if you've got 2 identical cars, right? One has just simply it's a scale up, like it's a higher horsepower engine. That's an option, and that just means that that particular engine or that particular version of the car will accelerate faster, right? It would get it up to speed faster. It's related. Torque and horsepower are related, yeah. Because not usually the bigger horsepower engines tend to be in bigger vehicles, right? Like it's not often that you've got like a 140 horses or 180 horses in the same car, right? Mustangs, you might that kind of thing, but trucks generally tend to be, right? Yeah. Yeah. A person is also a machine that has a power rating. Some people are more powerful than others. That is, they're capable of doing the same amount of work in less time or more work in the same amount of time. In the personal power lab, students determine their own personal power by doing work on their bodies to elevate it up a flight of stairs. By measuring the force, displacement, and time, we were able to measure our personal power rating. Suppose that Ben Pump-and-Iron elevates the 80-kilogram body up a 2-meter stairwell in 1.8 seconds. Now, Quinn has already measured the stairs for you at 2.58 meters. Just the bottom stairs, too, right, Quinn? Just the bottom section. You don't have to do the top section. If this were the case, then we could calculate Ben's power rate. It can be assumed that Ben must apply an 800 newton downward force upon the stairs to elevate his body. How did they get 800 newtons? They took 80 kilograms and multiplied by? They multiplied by 10 instead of 9.8. That's how they got the 800. Yeah, it's kind of lame. By doing so, the stairs would push upward on Ben's body with just enough force to lift his body up the stairs. It can also be assumed that the angle between the force of the stairs on Ben and Ben's displacement is 0. We're going to assume he's pushing straight up. With these 2 approximations, Ben's power rating could be determined as 800 newtons times 2 meters of distance divided by 1.8 seconds, or 889 watts. Ben's power rating is 889. What a horse. No, not that funny at all. The expression for power is work divided by time. Now, since the expression for work is force times displacement, the expression for power can be rewritten as force times displacement divided by time. And this is where we end up with that formula, power equals force times velocity as well. So you could actually figure out, given your power rating that you're going to figure out as you run up the stairs, you should know the force because it's equivalent to your weight. You should be able to calculate the speed that you actually climb the stairs, right? I wonder how.
So we do like directions and stuff.
Yeah, there's a probably. But it'd be interesting to see what happens if you took your weight, the distance, if you took the distance 2.58 divided by the time. No, I guess you're going to get the same thing, right? Because it's exactly the same. Yes, you're going to get the same number. But you can figure out how fast you're going. All right. The new expression for power reveals that a powerful machine is both strong, big force, and fast. The powerful car engine is strong and fast. The powerful farm equipment is strong and fast. The powerful weightlifters are strong and fast. Powerful linemen on a football team are strong and fast. A machine which is strong enough to apply a big force to cause a displacement in a small amount of time is a powerful machine. So there's an 8-question little quiz there on work and power. And then I guess I'll have to give you time to, those of you if you haven't run the stairs, you need to do so. If you haven't started your video, you need to do so. I will start Kinetic Energy Monday, I guess. You don't have your shoes today?
Well, Monday was school.
Tuesday. Alrighty, so let's see how we did here. Correct answer, 2 physics students, Will and Abel, Ben, Pump and Iron, are in the weightlifting room. Will lifts the 100-pound barbell over his head 10 times in a minute. Ben lifts it 10 times in 10 seconds. Which student does the most work? Same amount. C. Divas can't do. Maybe you can't do. Maybe that's what the person meant. I don't know. Correct answer is C. They do the same amount of work. Which student delivers the most power? B. Ben. How come? Does it faster. He does it in 10 seconds. During a physics lab, Jack and Jill ran up the hill. Jack is twice as massive as Jill, but Jill ascends the same distance in half the time. Who did the most work? A little trick at you here. It is A. Jack. Why is it Jack?
Weighs more.
He weighs more. Does the work have anything to do with the time? No. It only matters is that he's bigger. He's going to need more force. More work.
Why?
More force. Jack. However, who delivered the most power? They are the same. Mary, why are they the same? I know. That's why I'm calling on her. Why are they the same? Why are they the same? Because Jack is twice as big, but Jill does it half the time. Half the time. So they have the same amount of power. Okay? So in our situation here, for example, if I use, say, Quinn and Taylor as examples here, if Quinn happens to be twice as massive as Taylor, she would have to run up the stairs in half the time that Quinn would have to have the same amount of power. Power. A tired squirrel of mass of approximately 1 kilogram does push-ups. Have you ever seen squirrels do push-ups? Have you? I never have.
What if they're laying down and trying to get them?
Well, I guess. Yeah. I mean, squirrels got exercise too, you know.
I think that's the first time we ever gotten 100 on the question.
Yeah. By applying, you guys did well this. All the work in 2 seconds determined the power. So how would we have done this here? We've got the joules. It's just 0.5 divided by 2, isn't it? 0.25. Joules is energy. Or work. When doing a chin-up, a physics student lifts her 42 kilogram body a distance of 0.25 meters in 2 seconds. What is the power delivered?
I rounded it to 51.6.
Got around properly.
I did.
Did you?
Yeah.
So it'd be 42 kilograms times the distance of 0.25.
It was 51.
Times 9.8, right?
0.57.
Divide by 2, 51.5. Your household's monthly electric bill is often expressed in kilowatt hours. 1 kilowatt hour is the amount of energy delivered by the flow of 1 kilowatt of electricity for an hour, or 1,000 joules per second, as we pointed out on the board. So it's basically just 1,000 joules per second times 3,600 seconds, which of course, Zach, is 3,600,000, exactly. 3,600,000 joules of energy is 1 kilowatt hour.
That's on the board. If you better draw.
An escalator is used to move 20 passengers every minute from the first floor of a department store to the second. The second floor is located 5.2 meters above the first.
933.
The average passenger mass is 54.9. Determine the power requirement. I don't think that has anything to do with it. Determine the power requirement of the escalator in order to move this number of passengers in this amount of time.
What are the answers?
So the answers is 933.
Wow.
932.6. 32.
Round to nearest whole number.
Well, it's not reading. That's gay.
I gotta get a symbol in here so I can do it. Alright, so yeah, I would really like to start kinetic energy. How many people have not even started the personal power lab? Okay, you guys need to get your groups together and you need to do that.
How am I going to run it?
What are you wearing, Zach?